So basically in the fourth unit we will be dealing with the different structures of IIR and FIR filters, like how an FIR filters or IIR filters can be designed so that we can minimize the number of hardwares that can be used for designing these type of filters. Okay, so the basic components that we will be using to design IIR or FIR system are basically the adders, okay, and multipliers and the delay elements. So these are the three basic elements that are required to design an IIR or FIR systems. So once we have gone through uh, the structures, like how the IIR systems and FIR systems are represented, we can uh, have their expressions, like in what terms the IIR filters can be designed and in what terms the FIR filters will be defined. So the relation between the input and output gives the a system. Okay, so the same system that is explained or defined in terms of mathematics, we will be going to design the same system in terms of hardware now. Okay, so once we have studied the system in terms of mathematical expressions, there are different mathematical expressions for IIR systems and different for FIR systems, and these expressions will be in terms of their impulse responses. Okay, impulse responses or the transfer function. Okay, so in these we we will be having the transfer function of a system, and we will be going for designing its circuit diagram. In that circuit diagram, that will be in terms of the addition, number of additions required, number of multipliers required, and number of delay elements required. So any digital system is there that is represented in terms of difference equations. So these difference equations are like delay elements. Okay, so the delay element is represented by the your z inverse term, so that we will be dealing with the z transform of given time domain system. Once we will be converting time domain system to a z transform system, that is frequency domain system. As we have gone through the introduction, there are basically uh, three different type of representation, that is realizations of different systems, IIR and FIR systems. Here we will be dealing with the first type, that is direct form realization of a IIR system. So here we will be separately seeing the IIR system representation and the FIR system. So initially we are considering the IIR system realization. So any IIR system is given, we are going to realize that IIR system, that is the expression of that system in terms of hardware required, or in terms of arrangement of this hardware, like how we can obtain this particular equation or expression, so that we can use the minimum number of resources. Minimum number of resources means we will be requiring the minimum number of adders, multipliers and delay elements. Okay, so there are different forms or different representations. So one of that is direct form. Okay, so in direct form it is of two type, that is direct form 1 and direct form 2. Okay, so we will see one by one, like what is direct form 1 and what is direct form 2. So here this y of n, that is given by summation k equals to 1 to n ek y of n minus k plus summation k equals to 0 to m bk x n minus k. So here it is having this y of n is a system. Okay, so this is representing a system. So suppose this is a system, here some input will be given. Okay, so based on some input, some output we will be getting. Okay, so suppose this output we are getting is your y of n. Y of n is your output, and in the input part, if we are giving the input in terms of either x of n, delayed version of x of n, Okay, so either we are giving the present value, that means present value means it will be x of n. Okay, and if it is x of n minus k, that means we are giving the delayed version of x of n, so that will be considered as the past value. So x of n are, we will be providing it x of n minus k. Okay, so here any system to be stable, or that while analysis of any system we will be analyzing only that system that will be stable. And stable systems are basically a causal systems. So causal systems are the systems that depend only on the present value or the past values. Okay, so only the stable systems can be realized by a hardware. So to make sure, like we are going to implement, we are going to design the hardware of a given system, we should be making sure like the system is stable first of all. Okay, and in that stable system, it should be of the form like it should be causal system. Okay, so if it is causal system, it will be depending on the present value or the past values of input, or the past values of output also. So y of n is the output here, the y of n is the present value, whatever present value of the output, that is depending on the past values of the output also, and along with the present and past values of input. So this is the generalized equation uh, to any system. Okay, so any system that is defined, that is a stable system, that is a causal system, it will be given by the equation 1. Okay, so equation 1 defines the system that is a causal system, and which is only depending on the present and past values of your inputs. Okay, so once we have defined this, what we can do is uh, we will be separating it out. Okay, we will be separating the terms and terms by transform. So by taking the jet transform, we will define this. Okay, so once we have taken the jet transform, and then we will be dividing. So once we will take into jet transform, we will be dividing y of z divided by x of z, that will be giving you out the transfer function. Okay, so while realizing any system, IIR system, first of all we will be finding out the h of z, that means we need to find out the transfer function first. So once we have find out the transfer function, and that transfer function will be obtained by the given equation of a system. So from there we will be making y of z divided by x of z, that will be providing like summation of k equals to 0 to m. So here we can see like it is summation k equals to 0 to m bk x of n minus k. So it is x of n minus k, so its z transform will be, again the bk will be remaining the same. It is x n minus k is there, so it is minus k. Okay, so here k delayed function is there, so it will be z to the power minus k will be there. Okay, and x of z will be there. Okay, that will be in terms of the z transform. Okay, and similarly in terms of here also we will be considering, it will be y of z, y of z will be this for the z transform of this, and z transform of this will be summation k equals to 1 to n, ak will be same, y of n minus k will be having a z transform of z to the power minus k into y of z. Okay, so y of z we will be taking common. Okay, so here 1 minus this term will be there, so finally the transfer function will be given by this. So this is the transfer function of IIR system. So IIR system are basically the systems that will be having infinite number of samples, and that infinite number of samples should be of the form like it represents a causal system, and it will be a stable system. Okay, so once we have got the transfer function of a IIR system, we have to realize this system, the transfer function system of IIR system, in the form of direct form 1. Okay, so To obtain this direct form 1, what we will doing, we will be making these two terms. So like it is the transfer function, this is the numerator one and this one is the denominator one. So numerator represents the poles, sorry, the numerator represents the zeros. So this upper term will be representing the zeros location, and the term that is down to the transfer function that is in the denominator part, that will be representing you the poles. Okay, so we will be separating it out into two terms. So we will be separating poles uh, out of it and the zeros out of it. Okay, so after representing these two separating, we will be making sure like w of n will be representing your zeros value. Okay, so w of n represents the upper part and y of n represents the, or you can say in that terms, if w of n will be this one, then y of n from the equation 1 will be given by this term plus w of n. So we will putting w of n value instead of this one, it will be like y, the first plus w of n. Okay, so whatever first term is there, that will be added with the w of n to get the value of y of n. So y of n will be given by the w of n term that will be added to the first term. Okay, so here this is the transfer function, here this is zeros and these are poles. So what we will be doing is, we will be making two parts, one is zeros, one is poles. So zeros will be represented in terms of this first term. Okay, so the first term of the direct form realization will be a zeros, and second term will be poles. Okay, so we will be making it first term to h1z, separating it out like h1z is there, and second we will be making it out h2 of z. Okay, h1 will be represented first, realized first, and then followed by the h2 term. So poles will be realized first, sorry, the zeros will be realized first and the poles will be realized after that, and we will be uh, making a series connection between these two, and we get the value of y of z. Okay, w of n that is represented between summation k equals to 0 to m bk x of n minus k. Okay, so once we are getting its transfer function in terms of jet transform, we will be making, so jet transform will be calculated for this. Okay, and then we will be getting w of z is equals to x of z into k equals to 0 to m bk into z to the power minus k. Okay, so this is your w of k. Similarly from there we can get y of z is equals to, this y of z will be here, summation k equals to 1 to n ak into z to the power minus k, and plus takes the w of n will be converted to w of z. Okay, so from there if we get the value of y of z, it will be w of z divided by this term. First of all, we will be realizing h1 of z. So okay, so h1 of z will be your w of z. So it will be in terms of this function. Okay, so after expanding it, if we expand this term, so it will be like k equals to 0 is there, so this b0 will be there, b0 z to the power 0, it is 1. Okay, so b0 into x of z will be there. Similarly, once we put the k equals to 1 2 and 3, we can proceed to find out the w of z. Okay, so to realize this, we have to first make uh, input. Okay, a black box will be there, input will be there, that is in terms of x of n. Okay, and we will be finally getting the y of n, that is our output. Okay, so input and output, in between that we have to represent the first term, the first stage, in terms of zeros representation. Okay, so this is the representing the zeros, we will be expanding it. Okay, so if we are going to expand it, we will be finding like b0 will be there. Okay, b0 x of n minus 0. Okay, so n minus 0 will be there because k equals to 0, plus b1 x of n minus 1. Okay, and so on, other terms will be there. Okay. So first of all, we will be realizing the first term, that is w of n is equals to b of 0 x of n minus 0. So it is like x of n term. Okay. So the first term is b0 multiplied by x of n. Then second term will be plus by x of. So to realize this, because this is first of all we will be realizing the zeros only. Okay. So from there the input will be this one x of n, and first term will be directly the xn multiplied by b0. Okay. So we will be having a constant multiplier b0. Okay. So x of n will be multiplied by b0, and that will be added to get the value of w of n. Okay, so w of n here, so that is equals to w of n. So whatever terms we will be adding, that will be resulting to w of n. So w of n first term is realized by x of n b0. Similarly, in the second term is b1, a constant, multiplied by x n minus 1. So a delayed version of x n is there. So xn is, this is the xn input. They will be using a delayed input, delayed response, this delay network, that is called, that is represented in terms of z to the power minus 1. Okay, so this z to the power minus 1 will be representing a delayed response or a delayed version of x of n. So here the output will be your x of n minus 1. Okay, so this is x of n minus 1, and we need to multiply it by b1. Okay, and then whatever result will be there, that will be added to whatever result obtained by the first term. Okay, similarly there are different terms, different delay elements will be there, and finally at the last it will be x of n minus k, n minus k, that k equals to n, capital N. Okay, so x of n minus n will be there, and here b of n will be multiplied, and then it will be again added to the previous term, and finally all are added, and that will be resulting to the w of n value. Okay, so this is how the zeros will be represented. So these are the zeros basically. Okay, so zeros will be represented here. So once we have obtained the w of n, we will be representing the second terms now. Okay, so into the second term. Okay, so here y of n, that will be of output, will be in terms of x of, sorry, the w of n will be as an input, and y of n minus k will be an input also. So these two inputs will be there. So output will be y of n. So at the output n, but the input is w of n. Okay, so w of n is an input, so it will be added, plus output will be obtained. This output is itself the delayed version of output. So this output will be delayed once, and y of n minus 1 will be there. So that will be multiplied by a1, because after expanding this one for k equals to 1, a1 will be multiplied by y of n minus 1. So y of n minus 1 will be multiplied by a1. So we can obtain, this will be a delayed version. So y of n minus 1, it will be multiplied by a1 and added to this one. Okay, so so this is how the representation of y of n will be there. So y of n will be deleted by once, y of n minus 1, that will be multiplied by a1, will be added to get the y of n itself. So okay, so finally at the last it will be y of n minus capital M. Okay, so it will be, sorry, if it is in terms of here, so it is capital N is there. Okay, so this capital N will be basically in reality it should be. Okay, so this representation is there if they have assumed m is equals to n. Okay, so it is correct now actually. If it is two different terms are there, m and n are there, so if it is m and n are equal, then only this will be the considered. So it has made m and n equals to, at the last it will be y of n minus capital N. Okay, so that will be multiplied n, that is a constant multiplier, and added to this, and we will be getting y of n. So this is called your direct form 1. So in direct form 1, we will be first realizing the zeros, and then we will be realizing the poles. Okay, okay, so it could be further realized. So this will be the final representation of direct form 1 realizer. Okay, so in direct form 1 realization, we can see this is the zeros, and this representation will be for the poles. That one thing we need to take care is, like, if this is the representation of a transfer function, then only that representation will be there. That means it will be of the form, this is the standard form, it will be 1 minus something summation value. Okay, so this minus will be there. If this minus is not there, we have to change the coefficients magnitude. Okay, so if it is minus, then in the representation part, the coefficients of the poles will be positive. Okay, but if that there, if instead of negative, if it is a positive sign, then we have to change the sign of the coefficients of the poles. Okay, so that will be clear by using the example we will be seeing. So suppose this is the example, we need to develop a direct form one realization of a difference equation. So suppose this is the difference equation given, and we have to realize the direct form one realization. Okay, so to realize this type of function, first of all what we need to do is we need to find out the transfer function. So to find out the transfer function, we have to separate y of n or y of z separately and x of z separately. Okay, so we have to separate these two terms, and once we have separated, we will be dividing this y of we will be dividing this y of z divided by x of z. That will be giving you the uh, transfer function. Okay, so we have to find out y of z and x of z. Okay, so by taking the z transform, we can see this y of n will be having the same y of n function will be there, but for b0 x of n, this z transform will be b0 x of z plus b1 x of n minus 1 is there, so it will be b1 z to the power minus 1 x of z. Okay, similarly if it is b2 x of n minus 2, so it will be b2. Okay, so it will be z to the power, it will be z to the power minus 2. Okay, and into x of z. So this is how the z transform will be transformed. The time domain system will be converted into the z transform system. So once we have converted, we will be separating the y of z term separately and x of z term separately, and we will be dividing y of z divided by x of z. Then we will obtain this as the transfer function. Okay, so once we have realized the transfer function, what we can do is the above part will be like it is a zeros. So if zeros is there, so these zeros will be represented by the first block. Okay, so the first step, the zeros representation, then second will be representing the poles. So for the realization of the zeros, so the first term is b0, so b0 will be directly a constant value, so x of z will be there, that will be multiplied by a constant b0. Then b1 is there, that will be a delayed version of x of n. Okay, so x of n is there, a delayed version, that will be to the power minus 1. Okay, so it will be multiplied by b1, a constant, this b1 is a constant, that will be multiplied and added. Similarly z to the power 2 is there, so two delay elements will be there, 3. So how many delay, maximum delay is z to the power minus 3, so we will be requiring three different delay elements to realize the zeros part. Okay, so zeros part will be realized by using three different delay elements. Similarly, once we have realized this, in the denominator part, the summation should be 1. The its standard form is this one, 1 minus something. Okay, but here it is represented in terms of positive, all the positives are there. So that means once we will be taking the negative sign outside, all the coefficients will be having a negative sign. Okay, so in realizing, if it is negative, it will be a positive, but if it is positive function, consider So this is realization of poles. So poles will be realized. The first term will be the constant one. So the second term will be j to the power minus 1. Deleted version will be multiplied by minus a one term, because it is we have to take the minus side. Okay, so if it is there is no minus, then we will be considering a minus into the coefficient. Then another delay, because j to the power 3 is there, minus 3 is there, that means 3 delay elements will be used. Okay, if it is having a further term like 5 or 4 or 5, then 5 delay elements will be realized used for realizing this system. The first delay term will be obtained, and it will be having a constant multiplier by minus a1 constant, that is coefficient, and will be added to get the realization of a poles. Okay, so once we have realized the zeros and poles, we will be getting the complete realization in the form of direct form 1. Okay, so this is a simple realization. The only difference we will be considering is the we need to note is like we need to see if there is a negative sign is there or not. Okay, if it is written in terms of standard form, we will be realizing the same. Otherwise, if it is not written in standard form, like it is in terms of positive, then we have to change the sign. Okay, so whatever coefficients are there into the uh, denominator, just in the general terms, we can see whatever sign. If it is negative, it will be we will be making the same term. If it is positive, we will be taking the negative sign. Okay. The another form is direct form 2. Okay, so the first term was the direct form 1. The second one is the direct form 2. So in the direct form 2, so any transfer function that will be given in terms of h of z. Okay, so this h of z will be again written in terms of h1 of z and h2 of z. Okay, so in the previous example, I have written h1z divided by h2 of z, but it was not h1z divided by h2z. It is h1z into h2z. So the first term will be giving you out the zeros into the direct form 1, and the second term was giving you out the poles in the direct form 1, but its opposite will be in terms of the direct form 2. So in direct form 2, the first term, that is h1z, will be representing the poles. Okay, so this h1z will be representing the poles. The poles are the term that is written in the denominator part. The h2z will be representing the zeros. Okay, so these are h2z is equals to zeros will be given. Okay, so this standard generalized form will be h1z, that will be representing the poles, and h2z, that will be representing the zeros. So this is how the change between direct form 1 and direct form 2 will be there. So all other methods are same. Okay, so in the same way, we have to realize, so whatever middle term is there, that is we are representing in terms of w of n. Okay, so h1 of z will be 1 upon this term, and we will be making it loud out like its output is given out to be w of n. So w of n will be equals to here k equals to 1 to n a k w of n minus k plus x of n. Similarly, the output, final output will be terms in terms of y of n, that will be in terms of w of n minus k. Okay, so here, if this is the form, from there we can get w of n by equation this, and similarly the y of n by equation this. Okay, so the first we will be realizing is the poles. So into the poles realization, so in the poles realization, once we will be expanding it. Okay, so input will be x of n always, and output will be always y of n, but the middle term will be y of w of n. Okay, so this w of n will be output. So from there, once we are multiplying, we can get like the always x of n term will be there, so it will be having a constant multiplier. This will be a constant multiplier, there will be no multiplier. One will be there because there is no coefficient to the x of n, x of z. Okay, and w of n is itself the first term itself, and the second term is delayed version of itself. Okay, so it is delayed version, so w of n will be delayed once and that will be having a coefficient a1. Okay, then 2 times delay and a2 will be multiplied, and similarly the n time delay it will be an. So the same shifting is taking place. So this was the pole representation. The pole representation will be realized first in that direct form 2. So the whole representation will be shifted. This one will be represented here. So this representation will be coming out to be this side, and this one will goes to this side. Okay, the same representation is there. Okay, so once we will be putting this structure, we will be obtaining. So once we have obtained this structure, so what is the difference between these two, direct form 1 and direct form 2 is, in direct form 1 we were first realizing the zeros, and then second we are realizing the poles. But in the direct form 2 we will be first realizing the poles, and then we will be realizing the zeros. So what is the difference of changing these representations? So the difference is, once we have realized this, so what we can see, like whatever w of n is there, we are making in the pole representation. So this is pole representation, so into the pole representation. Okay, so in pole 1 we are considering the wn and with its delayed version of w of n. Okay, so these are the delayed version of w of n. Okay, similarly in the zero side also, what we are doing is we are using the delayed version, and that delayed version is for the w of n itself. So w of n is delayed to obtain the w of n, that w of n delayed versions. Okay, so in the direct form 2 we can see, like in the poles also and in the zeros also, we are going to use the delayed version of w of n. So from there we have the advantage of, like we can minimize the number of delayed elements used for defining a particular structure. So here the same IIR filter or IIR can be represented by reducing the number of delayed elements, because in the both terms, in the poles and zeros, the both w of n delayed version is used. So we can combine it, we can make it a common delay function. Okay, instead of using this n terms here and n terms here, where two n terms are being used, what we can do is we can uh, combine it, and finally we can get this type of structure. Okay, so this type of structure represents the direct form 2 representation. Okay, so here if we see in terms of the number of delayed functions required is, okay, so here we can get the number of delayed functions that will be requiring is n. Okay, so in the previous one it was 2 of 2n. So here we will be requiring only the n number of delayed functions. Okay, so here we are even reducing the number of hardwares required, and also we are reducing the time consumption, or we can say we are reducing, we can minimize the time. Okay, and we are once we are reducing the number of hardwares, we are reducing the complexity. Okay, so this is how uh, the direct form 1 and the direct form 2 realizations can be having an advantage over the other representations. Okay, so in direct form 2 we are reducing the required number of hardwares in terms of delay elements. Okay, so based on that we will see an example, like how the direct form 1 and direct form 2 realizations can be done to third order IIR transfer function. So this third order means we are having z to the power 3. Okay, so to realize this in terms of z to the power, we have to make in terms of z to the power negative. Okay, so the generalized transfer function should be in terms of this. So like we should be writing the given transfer function starting with the constant, then with z to the power minus 1, minus 2, minus 3, like that, and similarly into the denominator 1 plus a1 j to the power minus 1 j to the power minus 2 j to the power minus 3. Okay, so we have to write in terms of this function. Okay, but this is the transfer function that is not in the standard format. So what we can do is we have to multiply the transfer function into the numerator and denominator by uh, 2 into j to the power minus 3. Actually, uh, it is zero point 0.5. The coefficients at the starting should be equals to 1. Okay, so if it is, the coefficient should be 1, so to we have to make the first term to be 1. Okay, so to make first term to be 1, what we can do is we can have uh, multiplication of 2 into z to the power minus 3 on the numerator and denominator, and once we will be multiplying this, we can get whatever numerator is there. In the denominator, the first term will be 1, and then plus, and whatever next terms are there. Okay, so this numerator, so this is your numerator, and whatever denominator is there, in the denominator it is represented in terms of 1 plus something. Okay, that is following the standard representation of a transfer function, IIR transfer function. So from there we can use this realization of the direct form 1 and direct form 2 realizations. Okay, so we can see if we can use 2 into j to the power minus 3. If we are going to use 2 into j to the power minus 3, what we can see is here 2 will be multiplied. Okay, j to the power minus 3 is there, that means j to the power minus 1 will be there. Okay, so in the numerator we can see, so it will be represented in terms of point 0.5, 0.56 j to the power minus 1 j to the power minus 1. The second term will be whatever coefficients are there, it will be j to the power minus 2, and then whatever coefficients are there, it will be j to the power minus 3. Okay, and divided by, okay. So one thing we can see into the generalized expressions here, b0 is there, so this b0 was multiplied by b0, this one term. Okay, but here this b0 term is actually 0 into that given example. So this is 0, then this representation or this connection will be connected to a 0, that means it is an open, there will be no connection between this terminal to this terminal. Okay, so into the example that is given here, the first term is 0, like z to the power 0 term is 0, so this 0 will be multiplied here. Okay, so a 0 multiplied will be there, so 0 multiplication means there is nothing, so that's why there will be no connection between these two nodes. Okay, so there will be no connection. Okay, and all other terms like it is 0.56, so 0.56, one delay will be there, two delay whatever coefficients are there, that will be there. After three delay, that will be the coefficient and added together to find out the zeros representation. Okay, so these are the zeros representation in direct form 1. Similarly, this is the pole representation. So in the pole representation, after multiplication by 2 into j to the power minus 3, these terms will be, this is the one term, and this is the second one delayed term. Okay, so there will be 0.6 will be there, so as it is positive, so in the representation it will be a negative term. Okay, similarly this will be a negative term because it is a positive. Similarly here it is negative, so it will be of the form a positive term. Okay, after delaying the y of n, and this is how the direct form 1 realization will be taking place. Similarly, to obtain the direct form 2 representations, what we can do is the same term, this term will be going towards this side. Okay, and this complete term will be coming out to be this side. Okay, so once we will be making it out, and we have to make the common delay elements. Okay, so this will be the same representation will be there. Okay, so this delay element will be there, this is the constants, the same constants will be there, and the same delay element will be shared here. Okay, and the first this term is will be 0, so here there will be no term, okay, because it is multiplied by 0. So we will be removing this term, and there will be a no connection between these two lines, okay, these two nodes basically. So once we have done this, and we can show like this is the direct form to realization of the given transfer function. Okay, so is it okay with everyone? Okay, so this is how the direct form 1 and direct form 2 of a given transfer function can be obtained. Okay. Similarly, there is another example. It is of the second order filter. It is the transfer function of a second order filter, and that is given in terms of y of n. That is given by 2b cos omega 0 y of n minus 1. Okay, so in terms of delayed version of y of n is there, okay, and present value of x of n and the past value of x of n. Okay. So this is a causal system, and we need to find out the direct form 1 representation and direct form 2 representation. So to find out the direct form 1 and direct form 2 representations, what we can do is, first of all, we need to convert this into z transform by y. By taking the z transform, we will be considering y of z. And similarly, here cos omega 0, that is having no function of n, okay, so that means it will be like behaving like a constant. So this 2b cos omega 0, that will be a constant, and we will have to convert this in terms of z transform, only y of minus 1. So it will be z to the power minus 1 y of z. Then same b square, this will be represented like z to the power minus 2 y of z. Similarly, all other terms will be represented. Here also it is a constant term, okay, so the same constant will be written. So from there we have to find out the h of z, that is y of z divided by x of z. So this is the transfer function. So into this transfer function, if this is direct form 1, then we have to represent transfer function in terms of h1z into h2z. Here h1z, this h1z will be representing your, okay, so your zeros will be represented by h1z. Similarly, the h2z will be represented in terms of the transfer function that is for the poles, like a 1 minus 2 sorry 2b cos omega naught k to the power minus 1 plus plus b square j to the power minus 2. So this is your h2 object will be there, and this is h1 object. So h1 object will be in terms of zeros, so we will be representing the 0. So this b cos omega naught will be like a constant, okay. So and this h2 object we have got. So from there we can find out the function to have that direct form 1 representation. So from there the direct form 1 representation will be obtained by this, okay. So this is how the direct form 1 representation will be taking place. So here this is the first term. So one is constant, another one is minus b cos omega naught. Same one delay, after one delay minus b cos omega naught will be the constant, and the first one will be the constant 1 multiplied, okay. So this is the first term. Slightly the poles, in the poles part, this is 1 minus something, and this is plus. So if it is minus, same constant positive sign will be there, okay. So positive sign will be there in the coefficients after one delay, and in the second one it is positive, so it will be in the negative form in the representation, the structure form. So this is how the direct form 1 representation can be done. Similarly, we can find out the direct form 2. So in the direct form 2, what we can do is we can interchange h1 and h2 by their different values, and then after combining the delay elements, number of delay elements, we can find out this as the uh, representation in terms of the direct form 2, okay. So there is no difference, it is just a representation.